Have you ever felt that this year's heat is unusually intense? It's not just your imagination. According to the latest report from the World Meteorological Organization, there is an 80% chance that global temperatures will hit new record highs again within the next 5 years. In other words, it could get even hotter. Hello, Earthlings. Welcome back to Deep Space Society. Some airports have had their runways cracked from extreme heat, and even the Eiffel Tower expanded and bent by nearly 20 centimeters. Meanwhile, in the Arctic, temperatures are rising 3.5 times faster than the global average. But while we worry that Earth might one day turn into a second Venus, there's an even more mind-bending scientific truth. We are currently living in a long ice age, specifically a relatively warm phase called an interglacial period. So when will the next glacial period arrive? To find the answer, we need to take you back millions of years to feel the pulse of Earth's climate and search for clues hidden in our planet's deep past. Here you will witness a grand, decisive chapter in Earth's history, the last great ice age. This journey will show you the extreme environments that life on Earth has endured. Over 100,000 years ago, many of Earth's ecosystems were reshaped by massive ice sheets, by piercing polar winds, and by barren, frozen landscapes. This was a glacial period, an age of cold that lasted thousands of years. When it ended, many iconic species mysteriously vanished, and their disappearance still puzzles scientists today. What you're experiencing today is not Earth's first ice age. In fact, Earth has gone through 5 major ice ages in total. So what do they all have in common? An ice age is a long-term period of extreme global cooling, often lasting millions or even tens of millions of years. This causes large parts of Earth's surface to be covered by ice sheets and glaciers. The most recent ice age began about 2.6 million years ago, during the beginning of the Pleistocene epoch. And here's the surprising part. We are still technically living in that same ice age today. Every ice age contains 2 alternating phases: cold glacial periods and warm interglacial periods. Right now, we are in the most recent interglacial period, which has already lasted about 11,000 years. So when people refer to the last ice age, they often mean the last glacial maximum. It began around 115,000 years ago and ended roughly 11,700 years ago. Here's another surprising fact. During the last glacial period, the global average temperature was only about 6 degrees Celsius lower than today. But even a small temperature difference can reshape the whole planet. A 6 degrees Celsius global drop means a massive loss of heat from the oceans, land, and atmosphere. During this time, 2 enormous ice sheets dominated Europe and North America: the Laurentide ice sheet and the Fennoscandian ice sheet. Much of Earth's water was locked inside these ice sheets, causing global sea levels to drop significantly. Most land was covered with tundra and cold grasslands. No single factor can fully explain why Earth plunges into glacial periods, but much can be understood by studying Earth's orbital cycles. In the 20th century, Serbian scientist Milutin Milankovic proposed a groundbreaking idea. Earth's long-term orbital variations are major drivers of climate change. These are now known as the Milankovitch cycles. Orbital eccentricity. This describes how stretched or circular Earth's orbit is. Gravitational pulls from Jupiter and Saturn can make Earth's orbit more elliptical. This cycle lasts roughly 100,000 years. When the orbit becomes highly elliptical, seasonal lengths change dramatically. Summers become longer and cooler, winters shorter and warmer. Axial tilt. The greater the tilt, the more extreme the seasons. This cycle lasts about 41,000 years. When the tilt is small, winters accumulate ice that summers cannot melt. This buildup can eventually trigger a glacial period. Axial precession. Earth isn't a perfect sphere. Its equator bulges outward. Gravitational forces from the sun and moon cause Earth to wobble like a spinning top. This wobble takes about 26,000 years to complete. These three cycles together shape Earth's long-term climate. They are remarkably accurate in predicting major ice ages, though shorter climate events can amplify or weaken their effects. Most of the last glacial period took place during the Pleistocene, which lasted from 2.6 million years ago to about 11,700 years ago. The Ice Age was the era of megafauna, and mega is no exaggeration. Some of the largest creatures weighed up to 4,500 kilograms. But why did so many Ice Age animals evolve to become huge? One explanation is Bergmann's rule, which states that warm-blooded animals tend to grow larger in colder environments because larger bodies lose heat more slowly. This may partly explain why so many massive, awe-inspiring species emerged. Being large was a common survival strategy, but different species evolved different ways to survive the cold. Let's start with the most iconic Ice Age animal, mammoths. For most people, the woolly mammoth is the symbol of the Ice Age, a towering giant marching through deep snow, unbothered by the cold. But reality was a bit different. Mammoths were not actually much larger than modern elephants. Measurements show their shoulder height averaged around 3.5 meters, while today's male African elephants can reach up to 4 meters. Despite similar size, mammoths had key adaptations for the cold. They had a double-layered coat, a dense underfur, and a longer outer coat for insulation. Their bodies were longer and their legs shorter, which helped them graze without bending too much. They also had a fat layer up to 9 centimeters thick and small fur-covered ears to reduce heat loss. Humans have long attempted to bring mammoths back to life, but eventually they went extinct. However, they did not all disappear at the same time. A small population, about 500 to 1,000 mammoths, survived on Wrangel Island until just 4,000 years ago. That's 1,000 years after the Great Pyramid of Giza was built, glyptodons. Next is an even stranger creature, the glyptodon. Their name means carved tooth because of their wide, grooved molars designed for grinding tough plants. They were massive and tank-like, weighing up to 2 tons. With elephant-thick legs, they roamed the Americas, and their bodies were protected by a dome shell, making them resemble giant armadillos. But unlike armadillos, they couldn't curl into a ball. Despite their bulky appearance, they were not slow. Recent studies suggest they could shift much of their weight onto their hind legs and may have even stood upright. This creates an incredible image, a giant glyptodon rising up to defend itself or reach for food. These animals were far more capable than they looked giant ground sloths. This next animal might surprise you because their relatives are still alive today, but the modern ones are just a tiny fraction of their former glory. During the late Pleistocene, there were 4 major families, 27 genera, and countless species of giant sloths. They were great wanderers, traveling across the Americas over time. They grew larger and larger, eventually evolving into the giant ground sloths. One species, Megatherium, combined the height of a giraffe with the mass of an elephant. Some individuals weighed as much as 3,800 kilograms. Modern sloths are tiny compared to these giants. Many giant sloths dug enormous burrows, some large enough for a car to drive through. Why dig such huge tunnels? Scientists believe they did it for warmth, for shade during heat waves, or to hide from predators. Which raises an interesting question. What kind of predator would dare attack a giant sloth? Likely candidates include saber-toothed cats and the giant short-faced bear. Witnessing these massive and resilient creatures face extreme climates, powerful predators, and dramatic environmental change, you'd expect them to survive into the next geological era using pure instinct. But that's not what happened. Near the end of the Pleistocene, these giants vanished almost without warning, In regions like Australia and the Americas, between 72% and 88% of all large animal species went extinct. How could something so drastic happen, and why? For nearly a century, scientists have debated this fiercely. One major theory is that natural climate change was the main cause. As the interglacial period arrived, sea levels rose, land bridges disappeared, and massive ice sheets melted. This disrupted migration routes that many species depended on. But this explanation isn't perfect, because some populations, like the mammoths on Wrangel Island, survived thousands of years after the transition. Another theory emerged in the 1960s, pointing toward a new factor: ES. This brings us to a turning point in your journey. The moment you encounter our own ancestors, Homo sapiens. Homo sapiens evolved around 300,000 years ago in Africa and gradually spread across the globe. This means humans lived side by side with Ice Age giants for a very long time. So scientists began asking, were we responsible for their extinction? Could humans really challenge a mammoth or giant sloth? At first glance, it seems impossible. Homo sapiens evolved 300,000 years ago, but only around 50,000 years ago, during the Upper Paleolithic, did humans undergo a major cultural leap. Hunting and gathering reached new levels of sophistication. Tools became more advanced and diverse. People began creating ornaments like pendants and spent more time on activities beyond mere survival. Cave art became a way for humans to interpret their world, many of which remain visible to this day. By the late Paleolithic, rapid tool improvement made humans far more effective hunters. One human alone could not defeat a mammoth, but a coordinated group armed with spears could. Some spears could be thrown over 40 meters, turning the hunt into a fairer fight. One highly skilled hunting culture was the Clovis people, ancestors of Native Americans. Their weapons featured distinct stone spear points, called Clovis points. A major controversy arose because shortly after the Clovis arrived in North America, many megafauna species went extinct. This raised the question, did intense overhunting trigger population collapse? A recent study examined DNA from the only known Clovis individual, a child known as the Ansic child. It found that mammoth protein made up nearly 40% of his mother's diet. This strongly supports the idea that Clovis hunting contributed to megafauna extinction. In Australia, the pattern was similar. Around the time humans settled the continent, about 85% of all large species disappeared. Paleontologists studied fungal spores found in sediments, a proxy for megafauna population size. They found that within 4,000 years of human arrival, megafauna populations collapsed completely. The environment was changing before humans, but they were the final trigger. Another species that vanished in the late Pleistocene was the Neanderthals. They disappeared around 40,000 years ago. Neanderthals were the first humans to survive harsh glacial climates and had impressive adaptations. They were stocky, strong, and had large, high nasal passages to warm and humidify freezing air, similar to mammoth adaptations. Contrary to stereotypes, Neanderthals had complex culture, language capabilities, and sophisticated tools. So why did they disappear? Most scientists believe Homo sapiens outcompeted them, or absorbed them entirely through interbreeding. In fact, most people of Eurasian descent today carry 1 to 2% Neanderthal DNA, supporting the idea that they were assimilated, not simply wiped out. Their image as primitive or brutal is unfair. New discoveries continue to reveal their intelligence and culture. Without a doubt, the last ice age brought dramatic changes that permanently reshaped Earth's history. Despite the uncertainty of that era, many species thrived, adapted through both glacial and interglacial cycles. And as your thoughts return from the Ice Age back to the present, you can't help but feel awe at the sheer diversity life once had. Though those creatures now exist only as fossils, burrows, and remnants, they continue to spark our curiosity, hinting at a world where humans, giant beasts, and our extinct relatives once walked side by side across a wild, untamed Earth. Here's the unsettling truth. We are still living in an ice age today. A warm interglacial, yes, but an ice age nonetheless. So the real question becomes, is the next glacial period already on its way? Earlier we mentioned Heinrich events, massive climate disruptions that occur roughly every 10,000 years. They happen when enormous chunks of ice break off and flood into the oceans. Before each Heinrich event, ocean temperatures tend to warm, which destabilizes ice sheets and triggers their collapse. And today, we are seeing those warning signs again. If a Heinrich event occurred now, it could cool the planet significantly, potentially pushing Earth toward another glacial period. So when will the next ice age begin? The answer might no longer lie solely in the Milankovitch cycles. While natural forces are trying to pull Earth back into an ice age, human-driven warming is pushing the timeline in the opposite direction. Greenhouse gas emissions act like an invisible hand, shifting the schedule of the next glacial cycle into the unknown. If a new glacial period does arrive one day, which species will survive? Will Homo sapiens endure another world ruled by ice? Or will we be replaced by life better adapted to such conditions? And in the distant future, what will Earth look like? Who or what will call it home?